Today we're going to talk about the twin paradox. But first, what is time? It seems like a silly question to ask, but if I told you to define it, could you? Could you imagine some eternally ticking grandfather clock at the center of the universe, doling out a time for all that was and will be? Of course, no such clock exists, but the question remains, is there a time we can all agree on? Well, time is just a way of measuring the intervals between and the duration of events. If I played a few notes on the piano, you'd be able to tell me the order in which you heard them, and for how long you heard each of them. But how do we measure time? Well, think about a wristwatch. It's just a continual stream of events, the ticking of the second hand, that occur at the same distance apart. We just define one unit of time as the interval between each of these events. Then if we want to measure how long something takes, like how long until this video finally ends, we can just count the number of these events that have occurred. We're just constructing a ruler for time. But remember that we're trying to find a way to measure time that everyone will agree on. And certainly wristwatches aren't a very good way to do this. They're always out of sync. They never seem to agree with each other. Well, it turns out that everyone will agree on the speed of light. Believe it or not, this is a profound statement that has grand implications.
Let's use this fact to build a better way of measuring time. Suppose we have two mirrors spaced 1 meter apart and facing each other. If we shine a light onto one of the mirrors, then the light will bounce back and forth repeatedly between the mirrors. To measure time, we can just stand next to the mirrors and count the number of times the light bounces back and forth. Since everyone agrees on the speed of light, anyone else standing next to us will count the same number of times the light bounces back and forth, and so everyone will measure the same time. This is called a light clock. Now suppose you look at a light clock on a moving train. Since the train is moving, the light must travel a diagonal path so that it stays between the mirrors. That means it must travel a farther distance, greater than 1 meter. Additionally, if you have a twin standing on the train, then the clock on the train is stationary with respect to your twin, while the clock on the platform, next to you, is moving. So the converse holds for your twin on the train. They too will observe the light traveling a diagonal path greater than 1 meter. Now, let's focus on things from your point of view. In order for you to count the same number of oscillations on each clock, the light on the train's clock must travel a farther distance in the same time. The light must travel faster. Until Einstein came along, that is exactly what everyone thought, and it makes sense too. The speed of light on the train's clock is boosted by the movement of the train. But Einstein showed that this is not the case. Light must travel at the same speed as viewed by all observers.
It is instead our conception of time that doesn't match with reality. Since, as viewed by you, the light on the train must travel a farther distance, but is constrained to travel at the same speed, it follows that you will count a fewer number of oscillations on the train's light clock. Thus, you measure time on the train as running slower than time on the platform. Conversely, your twin measures time running slower on the platform than on the train, since, with respect to them, the clock on the platform is moving, while the clock on the train is stationary. This is an effect known as time dilation. Clocks are measured to run slower while you move in the frame. So we've shown that there is no absolute time upon which everyone will agree. Crazy, right?
Don't believe it? Well, if we haven't convinced you, try it for yourself. Let's make our own light clock using a tennis ball. First, simply throw the ball up and down while standing still. Now, walk at a steady rate and throw the ball up and down. The ball still lands in your hand, and to you, the ball is still simply moving up and down in a straight line. But, to someone else who is standing still, the ball traces out a parabola. This is a prime example of how events can appear different to observers in different reference frames.
But what about those twins? If each one thinks that time is running slower for the other, what happens when they reunite? They each think a different amount of time has passed. Let's look at a similar idea, but in a slightly different setting. Instead of a train, let's put one of the twins on a very fast spaceship traveling to a faraway star, leaving his brother here on Earth. When the traveler comes back to Earth, can the twins be the same age? This premise is called the twin paradox. Each twin thinks that time for the other person is moving more slowly. Like on the train and on the train platform, each person thinks that time is moving at a slower speed in the other frame. Let's take a look at our twins' journey.
Guess this is it. You excited?
It's only been my dream for years.
Will you send me a message every year?
Of course, although I expect you to do the same.
And how far away is it again?
About 10 light years each way, or 30 trillion kilometers.
It's pretty far. Will we still be twins when you get back, right?
You know, I never took intro to modern physics.
Yeah, you know, honestly, I don't know how you got to be an astronaut, but I will miss you. I will miss you.
I would miss me too. I have to go now, though.
I'm sorry, Dave. I can't let you do that.
What?
2001: A Space Odyssey? Are you kidding me? You're an astronaut and you've never seen 2001: A Space Odyssey? I mean, it was made 100 years ago, but it's still a classic.
Bye, Bo.
Bye, Dan.
Whoa! That guy just disappeared!
And cut. A spacetime diagram is a way to visualize how an object moves through space and time. We can see the path of the object in a way similar to how we can see the path of an airplane from the trail of the smoke it leaves behind. Spacetime diagrams are two-dimensional, so we plot them on the rectangular coordinate system. The x-axis of this coordinate system will measure the distance traveled by the object, the space component of the spacetime diagram, while the y-axis will measure the time that has passed the object, the time component. Together, these form the spacetime diagram. Now, suppose we want to measure distance in meters. And we can measure time in meters too. How, you might ask? Well, we can define the time in meters to be the distance a flash of light will travel in that time. So distance in meters can be associated with time by multiplying all times by the speed of light, c. C being this really large number. We do something similar to this all the time. When we're driving, we might say, the restaurant is 15 minutes away. We're saying that the restaurant is the distance away that the car will travel in 15 minutes. And at any given moment, the object is at a certain point in space and time. And so an event can be drawn on the space-time diagram with a simple dot. When an object isn't moving, it traces out a vertical path on the space-time diagram. When an object is moving with a constant velocity, it would trace out a straight line. And when an object is accelerating, it would trace out a curved path. These lines are called world lines. Imagine a beam of light traveling for 1 year. This will travel 1 light year on our x-axis, tracing out a world line with a slope of 1.
Who's there?
It's me, Dan.
Dan? Come closer. It's your skin. It's so smooth. You're so young.
You look old.
But it's been 50 years.
It's only been 7 for me.
Well, I'll be. The laws of physics hold.
I should have taken that class after all.
Come meet my grandchildren.
You're serious?
Yes, I'm serious. Come.
Let's take a closer look at what happened. We'll start by checking the world lines in our space-time diagram. Bo is traced out by this vertical line, since he stays in the Earth's initial reference frame. Dan moves at a path close to the speed of light, and then comes back to Earth's initial reference frame. For the sake of clarity, we're taking a look at a simplified version of this same effect with fewer lines and no numbers. If Bo and Dan send messages to each other once a year, then the messages will trace out straight lines with a slope of 1. In the beginning, there is a symmetry in which each believes himself to be the older twin. This is consistent with the fact that one cannot measure an absolute inertial frame of reference. In the middle, however, the frames of Dan and Bo aren't symmetric. Dan immediately begins to receive messages with a higher frequency as soon as he changes direction, but Bo doesn't begin to receive messages at a higher frequency until much later. This means that Bo doesn't see Dan change direction until much later because Dan is so far away when it happens. This can help us conclude that Dan is in the non-inertial reference frame. Thus, the experiences are no longer symmetric, because Bo only experiences one inertial frame, that of Earth, while Dan changes his inertial reference frame halfway through his journey. Dan will know that he is accelerating, either from the force he feels on his body or by the objects crashing into the walls of the spaceship as everything changes direction, and then know that time dilation cannot be applied to his view of Bo. Only clocks that are moving with respect to an inertial system will be observed to be running slower. Dan's frame is not inertial, so time dilation will only slow time for Dan. Using special relativity, Dan could in fact deduce that he will arrive younger. The twin who experiences acceleration will age more slowly, and thus there is in fact no paradox at all. Dan is the younger twin.
Oh wait, this is a cool one. Hang on.
What the fuck?
Oh, wow.
It's called Factory.
That's crazy. Alright, you good?
So great. Could just
Oh
watch it
shit.
for hours.
Oh shit.